Hello, everyone. Good morning or evening, depending on where you are. It's the last edition of the tree mortality seminar for this year. Not the last one overall, but the last for this year. And we have again a talk focused a little bit more on remote sensing of disturbance and recovery. So just as a background, we are the International Tree Mortality Network, a group of people working on all questions related to tree mortality. You can find information on our homepage. Also, all the upcoming and past seminars are there with recordings of the talk. So today we will have Joanne White with us. Joanne is a geographer by training, did then a PhD, I think, in remote sensing from the University of Helsinki, now works at the Canadian Forest Service. And if you have read anything about disturbances in Canada, you probably have read something by Joanne, and I'm really excited to learn more about how you use long time series to understand the dynamics of forests. Joanne, the floor is yours, and please share your screen.
Thank you. Well, thank you very much, Cornelius, for the introduction and the opportunity to come and share some of our work. And thanks, everyone, for connecting and showing an interest. So today I want to talk about some of the things we've learned about using remote sensing to characterize post-disturbance forest recovery. And specifically, I'm really talking about stand replacing disturbances here, so harvest and wildfire. And I am focusing primarily on boreal forests as well. And so before I jump into this, I guess I always like to clarify what I mean by forest recovery, because this is a bit ambiguous. So unlike disturbances, which can be punctual in both space and time, forest recovery is really a process and not a state. And the composition, the structure, the function of forests can manifest gradually over time through successional processes that happen following a disturbance. But definitions of forest recovery are not universal. And the point in time at which we consider a forest to be recovered really depends on how we define recovery and the information need associated with our application. So what I mean by that, for example, are in a reclamation context where we may be primarily interested in the reestablishment of herbaceous vegetation. In a silviculture context, we may be looking primarily for the stocking density of trees of a particular species. And other applications for other ecosystem goods and services may have more functional definitions. So in our work, our definition of recovery is based on the FAO definition of forest, which is trees that are taller than 5 meters and with a canopy cover greater than 10%. Now, the reason we use this definition is because this determines when an area is classified as forest. And so we're interested in the return of trees. Ultimately, that's what we're interested in. And so clear definitions are important because they allow for measurable indicators of recovery. And these indicators can be compositional, they can be structural, or they can be functional. But measurable indicators lead us to objective assessments of how the forest is returning following the disturbance. If we think about this in a national context, of course, I've already mentioned we need a definition, we need measurable indicators. We also need nationally consistent observations. So in Canada, for example, we have a system where each jurisdiction, each province or territory has the mandate to manage the forests and is responsible for sustainable forest management. And each has a slightly different way of monitoring and collecting data. So nationally, we're interested in consistent observations. We also want data that's synoptic, spatially explicit, and spatially detailed to the extent that we're able to capture anthropogenic impacts on the landscape. We want the ability to undertake assessments of recovery that are wall-to-wall over large areas. Whatever we do needs to be cost efficient, obviously. And the key is that we want an objective assessment that's not subject to shifting baseline syndrome. For example, And we want a permanent record, ideally some kind of map that shows us where forests are recovering and where they're not. So what remote sensing tools can we use for this application if the context is national and large area? And the primary data source is optical time series from Earth observation satellites such as Landsat or Sentinel-2. LiDAR is also an option, as is digital photogrammetry for these large areas. And increasingly what we find is it's the synergy between LiDAR, whether that be from spaceborne or airborne platforms, and the optical time series data. Now, we've used Landsat data primarily for our work, and some of the advantages of Landsat, for those of you who aren't remote sensing people, is the data is open access. It has a spatial resolution that's capable of capturing anthropogenic impacts on the landscape at 30 meters. It currently has an 8-day revisit, so the temporal resolution helps us ensure that we get a cloud-free observation within the growing season for our observation. Landsat has a carefully curated archive that is at 30 meters since 1984, so that gives us 40 years of data to work with. The Landsat program has invested heavily in sensor cross-calibration, so ensuring the sort of longer-term radiometric fidelity of the data. And there are lots of automated pre-processing tools and analysis-ready data products, including surface reflectance products that we can make use of. So one of the time series data have been one of the key innovations in remote sensing science. It's allowed us to move from this paradigm, scene-based paradigm where we're working with the best available image, to now a pixel-based paradigm where we're working with the best available pixel. This allows us to generate sort of seasonal composites or annual composites of imagery, and all of this has been enabled by increased computational capacity. What we can do with this data then is generate these best available pixel annual surface reflectance composites over these large areas. But these are not just pretty images, they're actually physical values. They represent observations that we can use to measure changes in phenomena over time. So this is an example, we need to update this, but this is an example of time series of best available pixel composites that we've generated through the National Terrestrial Ecosystem Monitoring Project for Canada. So how we use these data to monitor forest recovery, and why we use them, is that they give us these nationally consistent observations on an annual time step. Critically, they allow us to go back in time to do retrospective assessments and establish baselines. What is our expectation for how forests have been returning following disturbances that happened 40 years ago? And it allows us to integrate easily with other data sources, as I mentioned, such as airborne laser scanning data or field plots, into a monitoring framework. So we use these data to map disturbance, and we're able to do this quite accurately in terms of the geometry, the timing of the disturbance, but also attribution to a disturbance type, and in an automated way that's done nationally. And this is a real innovation for forest recovery in particular, because it allows us to differentiate between areas impacted by fire and areas impacted by harvesting. So what time series has really done for recovery assessments has really allowed us to, I like to say, close the loop. So for a long time, remote sensing science focused almost exclusively on disturbance detection and change detection. And time series data have really allowed us to take a much more holistic view of what's happening in the forest. And this is important for many things, but forest dynamics, forest demographic models, sustainable forest management, obviously, and for assessing the impacts of disturbances, among others. So for non-remote sensing people, what are we actually measuring with these data? Well, we're measuring reflected light energy from the forest, and we're measuring it at different wavelengths, and we're taking advantage of the different spectral responses that vegetation and bare soil, in the case of stand replacing disturbances, will have at different wavelengths of the electromagnetic spectrum. And we do this through using indices. And in our work, we've used a particular index quite extensively. It's called the normalized burn ratio. And it takes advantage of the different responses that vegetation and bare soil have in the near infrared and shortwave infrared wavelengths. What we find is that with increasing time since disturbance, we have a marked increase in reflectance in both the shortwave infrared and near infrared bands. And that initial sort of 20 to 30 year period following the disturbance, stand replacing disturbance, are then characterized by this increase in the proportion of sunlit crowns and a decrease in sunlit and shaded ground. So we see increasing canopy complexity and shadowing, and we're getting an increase in reflectance in the near infrared and a decrease in the shortwave infrared. So how do we translate this into a measure of spectral recovery? Well, we develop metrics from these indices that we can use to do this. So we have one particular index that we use. It's called the years to recovery metric. And we calculate this based on a pre-disturbance value from that normalized burn ratio. We measure the change magnitude, so the amount that spectral index changes over time. And then we measure how long, so in years, how long does it take for that spectral index to return to 80% of what its pre-disturbance value was. And in this example you see here, we see at C, it took 10 years for this particular pixel to return to 80% of its pre-disturbance value. We can, however, also measure and report as a continuous variable how that pixel has progressed relative to its pre-disturbance value. And say at the end of the time series, in this case, at 21 years post-disturbance, we see that it's 103% of what it was prior to the disturbance. So that's how we're assessing spectral recovery. Now, this doesn't mean that prior to the availability of Landsat time series data, no one was working on this topic and there was absolutely no research happening. There's actually a fair bit happening at this time. But a lot of these studies were using coarser resolution data, and they only had a single scene to work with initially. So they were doing a space for time approach as a chronosequence. And I'm highlighting studies here that specifically have looked at a boreal forest. And so a number of these studies were done, most of these studies actually, were done in North American forests. This first study here in 1997 was done in the boreal forests of Alaska. These studies used AVHR data primarily at 1 kilometer and then also 8 kilometers. So in these studies, people were using NDVI, which is a different spectral index that uses information from different wavelengths and is more sensitive to the return of green vegetation to a site. They were using these to assess recovery, and they identified that in these earlier studies, there were differences between different regions. In this case, in this study that came in 2006, we see that in this case, the authors identified a much shorter recovery time than the 2003 study by Hickey et al. Again, using the same data, almost the same time period, different methods, and looking at different targets. So in the case of Hickey, they're looking at severely burned pixels, whereas in the 2006 study, they were looking at all types of burned pixels. In 2005, we actually have our first study that used Landsat time series data. This was in the boreal forests of Alaska. And a couple interesting things here. They were also using NDVI, but they found that it took 8 to 14 years for NDVI to return to what its pre-fire levels were. They found more rapid recovery in more severely burned areas, and that recovery rate varied by forest type. The first study to actually look at boreal forests outside of North America in a recovery context was then this study in 2009 that was done in the boreal forests of Siberia. And in this case, they found that it took more than 13 years for the NDVI to recover. And they had some hypotheses about perhaps that it was because in the boreal forests of Siberia, ground fires are more common than the crown fires in North American boreal forests, and also perhaps a function of different resolutions. And then there was another study that used a slightly different index, but working with similar wavelengths, found a similar value, and this is also in the boreal forests of North America. So what we learned from this, all these studies focused on post-fire recovery exclusively, so none of them looked at harvesting. And they used NDVI or a similar index. They were all sample-based or single scene studies, so they didn't have, they weren't synoptic necessarily over contiguous large areas. They're not wall-to-wall assessments, given the limitations of the data that they had available. In these cases, for the baseline, they were using unburned control regions in similar forest types, so not a pre-disturbance value because they didn't have a chronosequence available to them. They all had a relatively coarse spatial resolution and identified conflicting results regarding whether recovery rates varied by region or forest type. And all identified that there was more rapid recovery in more severely burned areas. So just keep that in mind as we go forward. So then what we see an opening of the Landsat archive in 2008, and that dramatically changed the amount of scientific research that was happening in this area. So you see in the black line there, just an explosion of research into the use of Landsat time series for recovery assessments. But in the boreal, which is shown in red there, still relatively less focus on that forest type, which is also interesting to keep in mind. So since Landsat's become available, there's been a plethora of studies that have looked at recovery in boreal forests, and I just want to walk through some of the contributions that we've had from these studies towards understanding what these recovery metrics mean, how we can use them, and what they tell us about how the forest is recovering. So many of these studies highlighted the importance of disturbance type. And I mentioned earlier that this capacity to automate the attribution of disturbances to a disturbance agent over very large areas has been a key innovation in remote sensing science, but also in recovery assessments as well. And just to show you an example of what I mean. So here's from work we've done in Canadian forests. This graph is showing all disturbances that occurred between 1985 and 2012. And on the x-axis here, we have that years to recovery metric. So that's just to remind you, that's the number of years it takes for a pixel to return to 80% of its pre-disturbance value. And what we can see here is that harvested areas by the end of the time series, 89% of areas impacted by harvesting had spectrally recovered, whereas only 67% of areas impacted by wildfire had spectrally recovered. And so on average, what we see is about 9 years it takes for forests to recover, about 6 years for harvest, and about 11 years for wildfire, with significant variation in those numbers, obviously, is indicated by the standard deviation there. We also found that recovery rates varied by ecozone. So these ecozones are areas of similar biophysical and climatological characteristics. And so we can summarize these data because they're wall-to-wall and spatially explicit. We can characterize these recovery rates by these different ecozones and see how differently the forest is recovering from different disturbances across the country. These studies have also highlighted the importance of time since disturbance in interpreting these recovery metrics. So if we go back to my example that I showed, and recall that this is showing all disturbances that occurred between 1985 and 2012. I should mention that when we do our analyses, we always try to leave like 5 years from the date of the last disturbance and the end of our time series, so that there's actually some time for some recovery to happen. So in this case, we're looking at all disturbances. If we only look at disturbances that occurred prior to 1990, we see that these two curves start to converge. And so given enough time, the wildfire areas will also achieve spectral recovery. It just takes them longer. And so by the end of the time series, harvesting that occurred prior to 1990, 98% of those areas had spectrally recovered, and 92% of areas impacted by wildfire. So it's important to consider the time, how much time has transpired when you're interpreting these recovery metrics. You recall that in the earlier work, the pre-Landsat era, if you will, several studies had identified that more severely burned areas had faster recovery. And so several studies that have been done with Landsat data have also looked at the impact of change magnitude or disturbance severity on these spectral recovery rates. And just to remind you that change magnitude is the difference in that index in the year in which the disturbance occurred. And actually what we found in our work, so a wall-to-wall assessment nationally, is that areas that are more severely impacted by disturbance, so they have a greater change magnitude, have longer recovery times for fire. We see less of an effect for harvesting, and we see less variation in change magnitude for harvesting as well. If we look at a similar scenario, but using an open source of plot measurements and just looking at areas that were impacted by fire, we see a similar trend in that areas that had not, so plots that had not recovered by the end of the time series had a much greater change magnitude associated with them. Studies have also identified the importance of pre-disturbance forest type on recovery rates. So again, this is based on wall-to-wall assessment for Canadian forests. We see that areas that were coniferous pre-fire have much greater, longer recovery times than areas that were broadleaf or mixedwood pre-fire. Now this aligns with what we'd expect with these forests, given how they regenerate and the different mechanisms that they use. But we also see that this difference is greater for areas that were impacted by wildfire than for areas impacted by harvest. And again, if we do the same assessment looking at plot data specifically, we see that the same pattern. So plots that were dominated by coniferous species have longer recovery times than plots that were broadleaf or mixedwood. We also know that the spectral index that's selected for the analysis is important for the recovery. So what we find, and I mentioned this earlier in that pre-Landsat work, is that certain indices are much more sensitive to the return of herbaceous vegetation at a site. And so they'll saturate, as we say the term, much more rapidly than indices that use different wavelengths of the spectrum that are less sensitive to that effect. So what you see here are the normalized burn ratio versus NDVI, versus another index called the tassel cap greenness, which almost 75% of pixels have recovered within 2 years, based on this analysis that was done in boreal forests. So the index, so the takeaway from this is that the spectral index that's used really has to align with your definition of recovery and what you're trying to measure. So if you're interested in the return of trees, probably NDVI or tassel cap greenness are not the most effective indices to be using. Conversely, if you're primarily interested in the return of herbaceous vegetation, then NDVI may be a very appropriate index to use. So it depends a lot on the definition that's applied. We also see differences in both long and short-term metrics and have used both in our work. So this graph really shows the impact of using a 5-year, a measure of recovery at a fixed interval, so at 5 years post-disturbance, versus this longer years to recovery metric that we're using, shown in orange. And what we found for a national wall-to-wall assessment for Canada's forests is that areas impacted by wildfire were less likely to achieve both short and long-term recovery, whereas wildfire areas were more likely to achieve short-term recovery and not long-term recovery, which is just the corollary of what I just said. We also see that we have areas where we have no short-term recovery, but long-term recovery is achieved, and then very minor small areas where there's no recovery whatsoever by the end of the time series. So several studies have taken advantage of the differences in these short and long-term metrics to better characterize what's happening with the return of forests. And the reason we care about this is we don't have, as I showed you with that earlier example about the importance of time since disturbance, we don't have 30 years of data after every disturbance. And it would be really useful if we knew that short-term recovery was actually indicative of what longer-term outcomes might be for forests. And so we've done some work to look at that. And indeed, we find that areas that have long-term recovery also have lower short-term recovery, particularly for areas that are harvested. So this index on the y-axis here is an absolute measure of recovery at 5 years. So this is certainly a topic which needs more investigation. Most studies have identified and highlighted the spatial variability in forest recovery, which probably we're all would expect as well, but it's great to be able to quantify that. We've also looked at temporal changes in recovery over time. So this particular study looked at short-term recovery at 5 years. And in this case, we found evidence that post-fire spectral recovery rates have accelerated over time in both the east and west taiga shield here, with both having a consistent positive trend, whereas in the boreal, these short-term recovery rates were highly variable over time, and there was no consistent positive or negative trend observed in those cases. Some studies have also investigated these spectral metrics with other types of data as a form of validation, if you will. So in our context, we ask the question, if we consider something to be spectrally recovered, has it achieved our benchmarks of canopy height and cover? And other definitions could obviously use other criteria. So it's really trying to figure out is if we say something is spectrally recovered, what's happening on the ground? Are there actually trees returning to these locations? The first study we did was in the boreal forests of southern Finland. These are looking only at post-harvest in intensively managed boreal forests. And overall, we found that 89% of pixels that we had considered as spectrally recovered had achieved benchmarks of both height and cover. If we look at this in a Canadian context and look at both harvest and wildfire, we see something quite different. So 57% of pixels that were considered spectrally recovered had achieved benchmarks of both height and cover. And we see that height benchmarks, so this dark orange here, were much more commonly achieved for wildfire areas. And we know from other studies that have been done that these relate strongly to residual structures that are left, residual trees that are left in the forest immediately after the fire and may not actually die for several years. And we see for harvesting as well that metrics of cover were much more commonly achieved than in areas of wildfire. It's important to note that these spectral indices we're using to measure recovery may return to pre-disturbance values once the canopies reach crown closure or sooner, but there still may be large differences in vertical structure, which is why it's really useful to include metrics of both height and cover for these assessments. We've also used field plot data to validate these. So we've looked at recovery across different productivity gradients. This was also done in Finland. What we found is that sites that were less productive, so these xeric sites, had longer recovery times on average than sites that were more productive. And we've also found, as I mentioned earlier, about the importance of composition. So we found that plots that had more deciduous in them had faster recovery than plots that had less deciduous in them as well. So we've also done an assessment using field measures in Canada. This was using an open set of field data. And what we find in this case is that changes in plots that experience an absolute decrease in total stem density post-fire had significantly longer spectral recovery, so about 17 years, compared to plots that experienced no change in stem density between pre and post-fire. So here we had plots where there were measurements before and after the fire. And similarly, we found that plots that had not spectrally recovered by the end of the time series were typically drier. They were located at higher elevations and they had experienced a greater change magnitude. So one of the great things about having these spatially explicit tools is it allows us to do these broad scale, national level assessments and to establish baselines. So we can establish an expectation of recovery, and then we can see how different ecozones are performing relative to that baseline. Now, we used ecozones, but because the data are spatially explicit, you could really do this for any spatial unit of interest. We can use spatial statistics as well to identify areas with significantly greater clustering of faster or slower recovery times relative to that baseline as well. What this figure is showing you is it's showing you areas that were significantly positively clustered on the landscape. So where there were areas that were slower or faster than the ecozone baseline. So not a national baseline in this case, a baseline relative to the ecozone. And what we see from this is that there are certain areas that are recovering more slowly for wildfire at the top here and for harvesting as well. And we also see areas that are recovering more quickly than what we would expect given the ecozone baseline calculated over the past 40 years of observations. So just to show you what this looks like up close. So here we have a specific fire event in the northern forest. And in panel B, you can see the year of the disturbance, which is 1987 in this case. And then in C, we have the spatial variability of that years to recovery metric. And then we can map where the significant positive spatial clusters, so the areas that are significantly slower than what we would expect for that ecozone. Now, this doesn't mean that these areas won't recover. It just means that for some reason, they're recovering slower than is typical or expected for this particular ecozone. So we've also investigated these hotspots of slower recovery with airborne LiDAR data to find out if there's actually a structural difference that manifests in these areas. And indeed, there is. So we find that areas that are identified as these significant slow hotspots are less likely to achieve benchmarks of canopy height or cover, particularly for stands that have rapid spectral recovery in these areas. So there is a structural difference that is happening there as well. So you may be asking yourself, this is interesting, but how could we actually make use of this information? And so one example I want to share is through Canada's carbon budget model. So one of the things that we've used these data for is with our national carbon budget model. Previously, we assumed that all burned areas immediately start to regrow from age 0, so the year after the disturbance, on whatever their pre-disturbance yield curve was. And so using the Y2R metric and the regional variability that we saw in this, we're able to construct a regeneration delay that is now applied, which varies by analysis unit. And the analysis units are spatial units that are defined by various factors relevant for the model. Because our data is spatially explicit, the carbon teams are able to use that data to calculate appropriate regeneration delays for each of their reconciliation units. The delay is actually derived from the 75th quantile of the Y2R metric within each of those analysis units, and it ranged from 5 to 19 years with an average of about 14 years. So to conclude then, just some key takeaways that I hope you get from this is that with Landsat time series and increasingly with the availability of Sentinel-2 and harmonized Landsat and Sentinel-2 products, we now have unprecedented capacity to characterize forest recovery following stand replacing disturbances with much greater spatial and temporal detail than was previously possible. The spectral recovery metrics that we derive from these time series data are, importantly, they're spatially explicit and they're temporally exhaustive. And they can be useful as an important monitoring tool, but they need to be augmented by airborne LiDAR, spaceborne LiDAR, or augmented by ground plot data. And most importantly, definitions of recovery have to be clear and measurable. And the definition should determine the most appropriate spectral indicator of recovery. We've learned that disturbance type, magnitude, time since disturbance, and the pre-disturbance forest conditions are critical for interpreting these post-disturbance measures of spectral recovery, and that the power of the Landsat data is really enabling these retrospective analyses, allowing us to define a baseline or an expectation and identify these spatial hotspots, and then further investigate what's driving the differences at these spatial locations. And lastly, the boreal forests remain relatively underrepresented in this scientific literature. I just want to acknowledge my colleagues that I've had the good fortune of collaborating with on this work, and I welcome any questions you have. Thank you.
Thanks a lot, Joanne. It was an amazing presentation and great overview of this field and all this work. We have now a series of questions, and please, for you watching, write your questions on the chat, and we'll be collecting them and asking as many questions as we can given the time. So I have a few questions to start with from Fiona Gregory. So the question is, why do you pick the 80% for threshold for recovery? And then another question is, what percent of these harvest areas are being replanted or subject to other silviculture interventions?
Right, so those are great questions. So we use 80% rather than 100%, say, for example, because we don't expect the forest to return necessarily to exactly what was there prior to the disturbance. And so we did some work at exploring different indices. And 80% is, I guess, a reasonable compromise as an indicator for that value. So there was some science behind that. It wasn't just something we picked randomly. In Canada, all harvested areas are mandated with regeneration obligations. So in some cases that is able to be achieved naturally, and in some cases planting is required. But I just want to add, that is a great question, because that's obviously one of the drivers that we see in that different response between wildfire and harvest. We harvest on the most productive sites, whereas we know that fire is indiscriminate, and so it will burn unproductive sites equally well. And obviously that's why we see a more rapid recovery in areas that are harvested, as a combination of these are more productive sites and they are being managed either through silvicultural intervention or some other mechanism to achieve the regeneration of trees more rapidly than areas that are burned.
Thank you. We have another question from Alessandra Brund. Sorry if I mispronounced the names here. So have you ever worked with Landtrendiar, disturbance, magnitude, timing, since disturbance, pre-disturbance conditions are all parameters derived by Landtrendiar? Or you work with different Landsat algorithms?
Yeah, so we use something that's quite similar to Landtrendiar. It's called the composite to change algorithm, and so it is very similar. It uses time series of the best available pixel composites to identify the trends and the breakpoints to detect the changes. So it's very similar to Landtrendiar, but it's called composite to change. Hermosia et al. 2016 would be the reference for that.
Thank you, and apologies for my complete ignorance on the remote sensing world.
No problem.
We have a question from Cornelius here. Would it make sense to look at multispectral recovery?
Can you clarify what you mean by that?
Yeah, maybe I can ask the question directly. So most of the time you focus only on one spectral index, right, NBR, but we would have like 6 spectral bands with Landsat or even more with Sentinel-2. Would it make sense to look kind of more on the multispectral room for recovery, so to take all the information and not only one spectral index into account?
Yeah, definitely. And I think there are people that are doing that type of work. I think so I think there, like in everything, I think there are advantages and challenges to doing that. I think with a single index, you understand how it's functioning, and you understand the different responses you're getting from the vegetation and the bare soil. And when you combine multiple indices that are sensitive to different features and are measuring different things, I think the interpretation of the outcomes becomes a bit more complicated. Say if you're using them in a situation where you're putting 6 different indices into an algorithm to measure recovery, think that the interpretation can be a bit more challenging, because certainly you will get a mixture of, well, there's herbaceous vegetation establishing at the site, and that will tell you something in the short term, and then other indices would be more useful, I guess, in the long term, totally depending on what your definition of recovery is and what you're trying to determine ultimately. But yes, people do use multiple indices at a given time for detection.
Thank you. So I have a question from Wan Liang. A recent publication in Nature Climate Change suggests that for fire occurring before 2000, the deciduous fraction is decreasing during recovery, suggesting evergreen fraction is increasing during post-recovery for old fire. Do you observe this in your study?
No, I would say in our work, self-replacement is the most common. So we haven't seen a change either way, really, in our data. So I think there's also an expectation out there that we're seeing a shift towards more broadleaf species post-fire as well, and that's not something that we've observed either in a significant way. So I'd say no.
Okay. Thank you. We have one more question from Rina. As you said earlier, little much have been studied on spectral recovery of broadleaf forest. However, of boreal forest, sorry. However, were you able to also come across regarding studies on spectral recovery for tropical forests? So the question is basically, what's the literature like in tropical forests? Rina is from the Philippines. If her name is suggesting that, basically, Philippines there.
Yeah, I think there definitely has been some work done in tropical forest. I think tropical forest would be similar to the boreal forest in terms of, if we look at the whole recovery literature, it's been less focused. I think temperate forests have really been a focus primarily. So there has been some work done in tropical forests. I think tropical forests would have some unique challenges just based on the data type being used. So optical data, more sensitive to clouds, harder to get cloud-free imagery, but also the rapidness with which tree vegetation can recover, and that signal can potentially saturate. So I think tropical forests are interesting because that's probably one scenario where you need to integrate more LiDAR data, for example, be it from spaceborne sensors. So that's a great application for JEDI data, for example, as well as other data types also.
Okay. So I think we have time for one more question. Yeah, so there's one question, actually, this is from me. So what's your hypothesis about the trade-off between shorter versus longer term recovery? Do you think that the systems are perhaps trapped in this long term, the ones that recover fast in the short term, are they trapped there? In kind of like in a stage of recovery that they cannot progress? Is that something that you've been observing?
Well, I think the short term versus long term is we see, I think the interesting thing from that is that we see pixels that recover or that don't recover in the short term, but do recover in the long term. So I think, again, it's that question of, given enough time, they will achieve that spectral recovery. Okay, so I think in that case, they just need more time. And I think anyone who works in this field knows how variable a recovery response can be, even from one valley to the next, even, really, right? It can be quite different. So I think what's needed is a better understanding of the linkage between short and long-term recovery rates, because I think if we can develop solid relationships between those, or a better understanding of those, then that gives us more capability to forecast to the future what recovery outcomes may be given certain scenarios. I don't know if I've fully answered your question, but I don't think that graph I showed you shows that sites have recovered in the short term, but not in the long term.
Okay.
I mean, the graph did show that, but you have to remember that that's only to the end of the time series we had available. So it doesn't mean that those areas will not recover in the long term. It means that they have not recovered yet in the long term, in a spectral sense. And obviously, ecologically, there's something going on there that's different from other areas.
Thank you very much. I think, yeah, I think that was all for today. I'm sorry if we missed any questions here. And thank you very much, Joanne, for this very nice presentation. And we don't have a confirmed date for our next presentation, but please follow us on Twitter and look at your emails, because you will get more information for our next presentation that will happen in January. Thank you very much, Joanne. It was a pleasure to have you here with us.
Thank you. Thanks, everyone. Bye.